Hello everyone, I'm Huang from Tsinghua University. I'm presenting today on behalf of my colleague Jian, whose travel plans are being held up by one extremely thorough reviewer. Now, let's take a look at his work, Stripeless Data Placement for Erasure-Coded in Memory Storage. Nowadays, many production node storage systems have a demand of storing many small objects in memory. There's increasing need of in-memory storage systems that store data in DRAM. Also, as the amount of data increases, these in-memory systems become distributed ones. Intuitively, distributed in-memory systems are used as volatile caches, but this is not that good. When a node fails, the data on it is lost. This forces clients to fall back to the backend storage, which can increase latency by 2 to 3 orders of magnitude. Indeed, a distributed in-memory storage system should incorporate some internal fault tolerance. Even if some nodes fail, the data can still be found within the system. Replication is a common strategy for fault tolerance. However, it is very expensive. The main reason is that high cost of DRAM, making it unacceptable to dedicate this premium resource to storing object replicas. Instead, we propose using erasure coding. It encodes data into parity chunks to reduce storage overhead. For example, here, 3 blue data chunks are encoded to create 1 orange parity chunk. If a data chunk is lost, it can be reconstructed from the remaining data and parity chunks. The entire group, the green box, is called a stripe. A stripe contains data and parity chunks with specific mathematical relationship among them. In a stripe, we use K to denote the number of data chunks and P to denote the number of parity chunks. The storage amplification factor is therefore 1 plus P divided K. However, in a read and write heavy in-memory storage system, erasure coding is unfortunately much slower than replication. The need of placing data into stripes can incur significant runtime overheads. We detail them as follows. Some storage systems split objects into data chunks and encode them together into stripes. A typical example is Ceph. The problem of this approach is its high I/O fan-out, given that the objects are small. It is unreasonable to access multiple nodes only for an object smaller than a kilobyte. Other systems do not split objects. They need to encode multiple objects in one stripe. To assign objects to stripes, some use a statically defined policy. A key drawback is that they lack flexibility because the static policy do not respect the storage system's current state. For example, if a few nodes temporarily slow down, these kind of systems can experience surging tail latencies. Finally, some systems dynamically assign objects to stripes. Usually, there is a proxy that intercepts all client requests and makes centralized decisions. However, the proxy can be a performance bottleneck and there is a single point of failure. In summary, no matter which approach we take, there are always some significant overheads. However, the root cause of all these problems is the stripe concept itself. Abandoning the stripe concept will eliminate these overheads. As far as we know, all existing erasure coding schemes are based on stripes. So, to design a stripeless code, we need to first imagine how it looks like. Intuitively, we may view erasure coding as extended replication. Data is first replicated, and the replicas are then encoded into parities. We will get something like the following if we remove the stripe concept from both steps. Each node independently selects backup nodes for each primary object and independently encodes object replicas it receives. There is no distributed coordination aside from the RPCs used in replication. However, naive implementation of this idea can lead to data loss. If 2 objects' primaries on 2 nodes are replicated to the same 2 nodes, the 2 related parities can become linearly correlated. Recovery can be impossible in this situation if the 2 primaries fail together. The solution is to avoid such a situation. That is, any two objects with different primary nodes must share up to one common backup node. Thus, failure recovery becomes possible. We formulate this requirement as follows. Define Bi as the set of backup nodes for node I. For any two nodes I and j, it is required that the intersection of Bi and Bj contains up to one element. Now, how do we find such sets? This is where my colleague Jian comes in. My brain was stuck, but for him, it's easy. And for good reason. He was a TA for combinatorics in Tsinghua for years. So he just said, that's a SBIBD, we need lambda equals 1. And just like that, the problem was mapped to a balanced, incomplete block design. A SBIBD with lambda equals 1 defines a collection of sets where the intersection size between any two sets is 1. This is what we want. Details about the SBIBD theory can be found in textbooks. Here, we skim over only the necessary parts. Here, we have V servers in our cluster, and we seek to replicate node i's primary objects to backup nodes Bi. This is viable because each primary data object is placed on k backup nodes, so k is our replication factor. Also, every node acts as a backup for k other nodes, fantastic for load balancing. And finally, different primary nodes have exactly one common backup node. This is a crucial guarantee for fault tolerance. Our policy is, for each object, its primary node arbitrarily chooses p plus 1 valid backup nodes for it and replicates the object to them. If node I receives one object for each node in Bi, it encodes the k replicas into a parity using XOR. To briefly show why this simple policy is correct, let's assume node 1 fails and we want to recover an object on it. Imagine me an adversarial who wants to prevent successful recovery. First of all, each failed replication target of node 1 can affect up to 2 parities of the desired object. One itself and another now encodes 2 failed objects. There cannot be a third one, since it will violate SBIBD's properties. As a result, one can always use some parity to directly recover the object, unless I use more than half of my node failure quota. The same property holds for all the other nodes in the cluster. As a result, if we allow a degraded recursion with depth 2, I will need another more than half of my node failure quota to prevent the recovery of that desired object. Since I do not have that much quota, I cannot prevent successful recovery. This shows that recovery is always possible, and our policy is correct. Despite the complex theory and proof, the implementation of our policy is rather simple. The I/O critical path works just like replication. The difference is that there is a background thread on each node that encodes object replicas into parities. The most significant advantage of our policy is its flexibility and independency. Specifically, for each object, its primary node can make arbitrary and independent decisions of its replication target nodes. Meanwhile, the drawbacks of our policy is also significant. First, note that there is an extra way of replication in the I/O path. So since we need p plus 1 replicas aside from the primary, this causes extra memory and network bandwidth usage. Second, as required by the SBIBD theory itself, there are rigid constraints on the cluster setup, for example, its size. Finally, recovery may become recursive and can be less performant in scenarios other than in memory storage for small objects. Nevertheless, the main contribution of this work is to reveal that the conventional stripe concept is not absolutely necessary. Certain mathematical structures may have developed new design spaces for erasure coding. We expect that further research can overcome limitations in this work with more clever designs. We implement our policy in an in-memory key-value store with around 16,000 lines of Rust code. The system is evaluated on a 16-node cluster on Cloud Lab. Micro-benchmark results show that our system, Nostor, delivers significantly higher throughput than existing EC systems when objects are small. Still, when objects are large, it may consume extra network bandwidth. Under Twitter's memcache trace, our system also delivers overall the best performance, similar to replication. Sometimes it even performs slightly better because it stores less redundant data, thus having much less memory pressure. Repairing is fast, and data transfer and encoding can be pipelined. There's no need to reconstruct exactly the same parities before the failure. Still, degraded read latency can be high if there's a recursion, but we believe it is still acceptable. That's all. Questions are welcome. For deeper combinatorial questions, well, we recommend mailing to the professional TA. Thank you very much.